Have you ever looked at one of those sheer mountain cliffs, the kind wrapped in storms, and just thought, there's no way? Well, some engineers look at that very same cliff and think, challenge accepted. Today, we're heading to the world's most brutal environments to see how humans build transportation systems that basically spit in the face of gravity, battle the elements, and operate right on the ragged edge of what we all think is possible.
I mean, just look at this. This is not science fiction. This is the Stoosbahn funicular in Switzerland. Those, futuristic-looking barrel cabins, they are climbing a track with a mind-boggling 110% gradient. To give you some perspective, a 45-degree angle is 100% gradient. This is steeper than that. This is literally a train that goes up a cliff. And honestly, it's just a taste of the incredible machines we're going to get into today. So, that brings us to the big question. How in the world do you actually build something like this? I mean, when your main opponents are physics itself, insane weather, and ground that's literally moving under your feet, what kind of thinking, what kind of tech does it take to actually win? To really appreciate these wild solutions, first, we've got to understand the villains of our story. See, engineers in these places face two relentless enemies: the crushing, sneaky power of ice and the simple, unforgiving pull of gravity on insanely steep slopes. Okay, first up, ice. And we are not talking about a little bit of frost you scrape off your car. This is atmospheric icing. It happens when supercooled water droplets, that's water that's been tricked into staying liquid below freezing, suddenly hits a surface and just flash freezes on impact. And it just builds layer after layer until everything is encased in this heavy, treacherous shell of ice. Now, what's really fascinating here is how ice attacks the system. It's not just one thing. First, you've got ice jacking. It's exactly like when you leave a water bottle in the freezer and it cracks the plastic. Now, just imagine that same force, but happening inside the concrete and steel of a massive support tower, cracking it from the inside out. Then there's something called galloping. The ice builds up unevenly, turning a perfectly round cable into this lopsided, unstable airplane wing. The wind catches it, and the whole cable starts thrashing violently. And of course, there's just the sheer brutal weight of it all. We're talking tons of extra load the system was never designed for. And let me be clear, this isn't just a theoretical problem on a whiteboard. These dangers are very, very real. Just back in 2022 on the Sandia Peak cable car in New Mexico, severe icing just stopped the system dead. 20 people were trapped in a cabin overnight in 20 below zero weather. The stakes here are as high as they get. Okay, time for villain number 2, incline. This number, 159%, that's the maximum gradient on the new Schilthornbahn in Switzerland. And let's be real, that number probably doesn't mean much on its own. So think about it this way. 100% gradient is a 45-degree angle. That is already incredibly steep. This is way, way beyond that. We are talking about a near vertical climb. And this is where the physics just gets terrifying. On a slope this steep, with a normal cable car design, gravity doesn't just pull the cabin straight down. It also pulls it backwards, tucking the top of the cabin scarily close to the main cables it's hanging from. Now, you throw in the high winds you always get in the Alps, and the slightest sway could cause a catastrophic collision. So yeah, those are the problems. Big ones. Now for the really cool part, the solutions. How have engineers actually fought back against this constant attack from alpine ice? Well, they've basically declared it a multi-front war. And you can meet the frontline soldier right here. This is a remotely operated vehicle, an ROV, built for one thing and one thing only: to find ice and destroy it. This little autonomous robot crawls along the rope like a tiny, determined icebreaker ship, and its whole mechanism just physically shatters and clears off the ice, making sure the line stays clean and, more importantly, safe. But you know what? The robot doesn't fight alone. Engineers throw a whole arsenal of tactics at this problem. They can shoot a high-frequency AC voltage through the cable, using something called dielectric heating. Just think of it like a very, very precise microwave for the cable itself, melting the ice from the inside out. They also use just simple brute force. They run the empty cars for an hour before opening just to knock all the ice off. They use common sense, parking the cabins in sheltered stations overnight so ice can't build up in the first place. And they use other mechanical de-icers that just scrape the cable clean as it runs by. All right, so the ice is more or less handled. But what about that other villain, gravity? How do you solve the problem of that absolutely terrifying 159% gradient? How do you conquer the vertical? Oh, this is just brilliant. The old way of doing things used a short arm to connect the cabin to the cable. And look, that's great for stability on normal slopes, but it's a total disaster on a 60-degree cliff face. So the new way? It's this simple, revolutionary, and completely counterintuitive idea. They added a massive 11-meter-long hanger arm. This thing acts like a giant lever, using the cabin's own weight to push itself out and safely away from the main cables, creating this huge safety buffer even on the steepest parts of the climb. And the results? Well, they speak for themselves. This single design change lets a cabin full of 85 people climb almost 800 vertical meters in under 4 minutes. And it does it with perfect stability, even in those harsh mountain winds. It's just an amazing testament to how changing the geometry can completely solve a massive physics problem. But what about that other marvel, the Stoosbahn? Its secret is every bit as clever. So as the train climbs, you've got sensors that are constantly checking the changing slope of the track. A hydraulic system then takes that info and automatically rotates each of the individual cylindrical cabins. What that means is, while the train itself is climbing a practically vertical track, the floor inside your cabin, the one you're standing on, stays perfectly, completely level for the entire trip. Look, the high-tech cars and the de-icing robots are obviously impressive. They get all the attention, but none of it would matter without the foundational engineering holding the whole show up. So now we're going to look at the unsung heroes of these systems, the towers that have to stand on moving ground, and the cables that are the literal lifelines of the entire operation. This might be one of the most mind-bending engineering challenges of all. You are looking at a huge steel support tower that is built directly on top of a glacier. But here's the thing, glaciers aren't static. They are slow-motion rivers of ice, and they flow downhill. This particular one moves as much as 10 meters, that's over 30 feet, every single year. How on earth do you anchor a structure to that? The answer is, you don't. You don't fight the glacier, you move with it. It's brilliant. The base of the tower is connected to its foundation with a gigantic hinge. So, as the glacier flows downhill, the tower is just allowed to slowly tilt along with it. Then, once a year, a crew comes in, detaches the whole thing, repositions the foundation, and straightens the tower back up for another year of slow, controlled movement. All right, let's talk about that lifeline itself. 70 tons. That is the weight of a single continuous piece of steel cable used on the Schulter-and-Bahn. 70 tons of braided steel. The process of creating something this strong and this big is an absolute engineering marvel all by itself. You don't just make a 70-ton lifeline, you forge it, and it's a multi-stage epic. It starts with a process called cold drawing, where steel rods are pulled through these special dies to align their internal crystal structure, which makes them insanely strong. Then, every single tiny filament gets coated in molten zinc, creating this impenetrable shield against rust. As those filaments are twisted together into bigger strands, high-pressure grease is injected right into the core, acting like a permanent internal lubricant. Then, those strands are compacted, squeezing out all the air to maximize the steel density. And finally, all of those massive strands are braided around a central steel core to create that 70-ton beast. So, after looking at all of these absolutely incredible feats of design and construction, what's the big picture here? What does this all really add up to? Well, we've basically seen a whole portfolio of heroic engineering, right? We've got autonomous robots that fight ice, brilliant geometric solutions like that 11-meter hanger arm, impossibly clever rotating cabins, and even foundations that have literally learned to go with the flow of a glacier. Each and every one is a direct, ingenious answer to a problem that seemed impossible. And it is so crucial to remember this. This matters so much more than just tourism. For a village like Mürren in Switzerland, which is completely car-free, this cable car is their only link to the outside world. It brings them food, it brings building materials, it gives them access to doctors. These systems are vital lifelines. They're powerful, moving monuments to human persistence and our absolute drive to overcome any obstacle thrown in our way. It really just leaves us with one final thought. The engineers who built these things, they solved the most extreme challenges of their day. But, in a world with a rapidly changing climate, what new, what unforeseen extremes will the next generation of engineers have to face? What impossible problems are waiting just over the horizon for them to solve?